function. So then we have 12.8 change of variables in multiple integral. Change of variable in multiple integrals. So, okay, see, in Calc 1, you had the concept of change of variable. You remember, and actually you used this concept several times. For example, in Calc 1, when you wanted, for example, to integrate from this function sine of 2x dx, we were told we define a new variable u equal 2x, and we had the concept of change of variable, and after that we find the answer. Today, we want to see that how we can change the variable if we have double integral, if we have triple integral. Then our goal today, and maybe tomorrow, we will continue this tomorrow, is to see how we can use change of variable if we have double integral, if we have triple integral. In order to explain this, first we need to start by one definition. See, suppose you have a two-dimensional shape in xy plane and uv plane. For example, we can have, I don't know, so one shape here and another shape here. Our goal is to define a transformation from this one to this one. Most people write in this way, t equal t of uv. Then see, you have one region in uy plane, and you have transformation t. By using transformation t, you can transform this region into this region. Most people write in this way. People write t of uv equal to x of uv comma y of uv. I am not sure how many of you have taken linear algebra, or this semester maybe you have linear algebra. These kind of transformations usually are studied in linear algebra. The in linear algebra, you have two-dimensional space. You have to, we can have more than two-dimensional space, 3 to 2, 2 to 3. But we define a special, in linear algebra, a special transformation between two vector spaces, but usually in linear algebra, we prefer to have linear transformation. But here, this transformation is not linear necessarily. I will explain what does it mean when we say linear. But see, for us, T is a transformation. By using this transformation, we can transform one region to another region. And usually we write this T as xuv, yuv, and here this guy is a two variable function, two variable functions. Two variable functions. Let's see, you have one region, you have another region. By using this transformation, you can transform one region to another. And here on x-axis, on y-axis, you have two variable functions. I know it sounds very odd, very strange. We will see more examples. But see, you can transform this. Then mostly people prefer to assume that x and y are two differentiable functions. Okay. So because I want to make this easier for you, then let me give you one example of u and v to understand what I'm saying. Let's see, for example, T of uv can be something like this. For example, u squared minus v squared, comma, 2uv. Then see, this guy is a function of uv. How many variables you have here? Two variables. Then this is x of u comma v. This guy is a function of uv. How many variables? Two variables. Y of v. Any question? Any question? Let's see, million functions with two variables can be written as the first coordinate and the second coordinate. The first coordinate and second coordinate can be million functions. This is one example. Is it linear? No. Why not? Because here we have power 2. When you are in linear algebra, when you are talking about transformations, you are talking about linear transformations. See, one linear transformation, for example, is this. TUV, this is 3U plus V. Okay. TUV, this is 3U plus V, comma, minus U plus V. These are two examples. Let's see, for example, here, this guy is X of UV. This guy is Y of. Okay. Okay. Then see, this guy is called linear transformation. Why? Because the highest power on U and V is 1 and you have no multiplication. Then something like this is called linear transformation. In linear algebra, people are interested in something, in functions like this. But this is also transformation, but it is not linear because you have power 2. Again, you can write million examples. These are just two examples. I just wanted to give you an example to show you this is not something very strange. Then see, when you have a transformation, it means you have a function with two variables, u and v, and here you have two more functions, and these functions are functions with two variables. Any question? Any question? Any question? Everybody is following what I'm saying? This is geometrically speaking, usually a region is given in UV space, and you want to convert into XY space. This guy is denoted by X, this guy is denoted by Y. Okay. Most people prefer to have differentiable functions here, because see, these are functions with two variables. Before the break, we have seen the concept of differentiable functions with two variables. Then mostly people prefer to have differentiable functions here. Okay. When you have a differentiable function here, if you read the book, you will see that these functions is called C1, C to the power of 1. I will write it, but this is not something new. This is just a notation for differentiable function. We have C0. C0 is continuous function. C1 is one time differentiability, and more than one time also can be written. But okay. So what I have done up to now, I just gave you two examples. That's it. Then I didn't teach anything hard up to now. The only thing that I said is this: you have a class of functions which is called transformations. Transformations are functions such that they have two components. Every component is a function with two variables. Any question? Then see, when we are talking about transformations, we are talking about functions with two components. Every component itself is a function with two variables. This is one example. This is another example. In linear algebra, when powers on u and v are 1, then these kind of functions are called linear. And this guy is linear, this guy is not linear. Any question? Any question? Any comment? Anything? Good. So then let me continue. Then we can write this definition. Transformation in R2 is a C1 function T from R2 to R2 such that T of U comma V is X of UV comma Y of UV where x and y are functions, two variable functions for sure. Functions. Okay. Again, what does it mean when we write C1? C1 means differentiable. Then C1 is a mathematical notation, which means differentiable. Differentiable. When people write 1 as the power, then it means 1 time differentiable. It's possible to have functions which are 2 times differentiable. And it is possible to have a function which is differentiable infinitely many times. When you have a function which is differentiable infinitely many times, we write c to the power of infinity. You see, this is actually very interesting space in geometry. You can see c to the power of infinity means functions which are infinitely many times differentiable. Then we have this. Okay, then we will never use this notation in this class. Don't worry, this is very abstract, pure mathematics here. Okay, but these are very famous actually space in pure mathematics. And actually, we have something like this. Then we have okay, never mind. Okay, never mind. Sorry. Any question? Any question? I'm not sure how much definition is clear for everyone. Then again, see. This x, u, y, you see, for example, this is x, u, v, this is y, u, v. For this example, this is x, u, v, this is y, u, v. Then something that I am saying is this. When you are talking about transformation, you are talking about a function. This function contains 2 components. Each component is a function with 2 variables. Let's see, this is one component, this is another component. Then this function contains 2 components. Question, comment, question. Again, because I want to make sure everybody is following what I'm saying. Let's see, for example, for this guy, if you want to find t at comma 1, 0. Let's see, if you want to find the value of this function at 1, 0, you just have to plug in 1, 0 here. Then this is 1 squared minus 0 squared, comma 2 times 0 times 1. Then this is 1, 0. Let's see, the value of this function at 1, 0 is 1, 0 itself. Let's see, and you can plug in other values and find value of this function and everything. The only difference between this function and 2 variable functions or 3 variable functions is this. When you had 2 variable functions, when you had 3 variable functions, the value of the function at a triple or at a couple is a single number, is a real number. But here, as you can see, the value of this function at a couple is another couple. Okay? Any question? Any question? Any question? Okay, good. So, okay, I would like to add one more definition here for transformations. Sorry, our class today is a little bit abstract. So then another definition, if no 2 points, have the same image, by t is called 1-to-1. Okay, so then when you have 1-to-1, let's see, you can have x, y, something like this. You can have uv, something like this. Then when you have a 1-to-1 transformation, you can define inverse of transformation. Let's see, this is t. This guy is inverse of t to the power of -1. And when you have 1-to-1 transformation, you can have inverse. It means that you can transform this region into this region. By using the inverse, you can come back. Okay. Any question? Any question? So I think it's enough for theory. Then let's solve one example. I'm sorry, that was too abstract, too theoretical. So then, okay, can I erase here? Okay. So then let's see. One example, then example, and transformation T is given as T of u comma y, u comma v equal to u squared minus v squared to uv. Find the image of S equal to 0, 1 times 0, 1. If somebody forgets the Cartesian, this one is called Cartesian product. If somebody forgets this concept, it means that here u is between 0, u is between 0, 1, v is between 0, 1. Then here, if I want to translate this into more understandable way, here it means u is between 0, 1, v is between 0, 1. And here, if I label this axis by u and this axis by v, then we can say S, as we have seen before at the beginning of this chapter, S is a square. S here is a square. Then what is my goal? My goal is to use this transformation, and we want to see that if we use this transformation, what is the transformed region for this square? Any question up to now? Any question? Any question? Any comment? Any question? Then see, okay, this is 0, 1, 0, 1. Then this is S. Geometrically speaking, you have a square, and your goal is to find the transformed region for S by using T equal. So, okay. See, yes, we will finish this question tomorrow. I'm sure that, you know, the class was tough enough. But before going, I want to explain something. See, usually people denote this guy by X and this guy by Y. And here what do we have? We can write X equal to u squared minus v squared and y equal to 2u. You see, we have x equal to u squared minus v squared, y equal to u. Then what is my goal? My goal is to see if we assume x equal to u squared v squared and y equal to 2uv. And if we assume u is between 0 and 1 and v is between 0 and 1, what is the bound for x and y? It means when we say u is between 0 and 1, v is between 0 and 1, we can say x is between what and what, y is between what and what. This is actually our goal. Then again, one more time, then look at my hand, then here, this is v. You can say that v is between 0 and 1. It means v is between these two horizontal lines. And u also is between 0 and 1. It means u is between these two vertical lines. The question is what we can say for x and y. What bounds can be found for x and y? X is between what and what? Y is between what and what? Another thing that I want to warn you about, here see the bounds that you have for u and v are constant. Here u is between 0 and 1.